let us now do some problem on the falling film. We have done this falling film. So, let us do some problem on that, and in that case you will be able to know and you will be able to find out this much better, that this we have done. Say an oil is flowing down a vertical wall as a film 1.7 millimeter thick. The oil density is 820 kg per meter cube and the viscosity is 0.2 Pascal seconds. Calculate the mass flow rate per unit width of wall, Reynolds number and average velocity. So, this is a then pure case of falling film, where we are saying that an oil is flowing down a vertical wall as a film 1.7 millimeter thick. So, thickness of the film is also given. That means, we have a vertical wall and down this wall a film is travelling like this. A film is travelling like this, right. Obviously, as we said earlier, that when it is happening, then there is some heating source also there, so that this concentration of the oil that can go up or film can go up. Density of the oil is 820 kg per meter cube and the viscosity is 0.2 Pascal second. Now, calculate the mass flow rate per unit width of wall, Reynolds number and average velocity, right. So, if this is the case, then we can say that mass flow rate as you remember, it was m dot, and we could find out from 2-3 relations we had. So, one such relation if we use, then it becomes del cube rho g over 3 nu, right, del cube rho g over 3 nu. So, this nu is equals to mu by rho, right. So, this nu equals to nu by rho, because whatever we had given earlier or we developed, it was like that, and if you see the unit, then it comes also like that. Let us see, this is millimeter or say meter cube, and say this is kg per meter cube, this is meter per second square. So, this is 3 and nu is viscosity by rho, that is we can say kg per kg meter per second, and density is kg per meter cube. So, this density goes out kg per meter cube, right. So, meter per second, this is meter cube, this is meter. So, it becomes per unit mass, right. So, we can say this second, this square goes out, and this meter, okay. So, it comes this kg should go up, right, kg per oh, this was kg per meter cube, right? So then it does not go out. Oh, so I made the mistake. So meter cube, right? So kg per meter cube, and this is meter per second square. Then this is kg meter per second and divided by kg per meter cube. So that means this is meter cube and this is kg per meter cube square, right? Kg per meter cube square, and this is meter per second square, and this is kg meter per second. So 1 second goes out, this 1 kg square goes out, 1 meter cube this goes out, right, and this meter and this meter goes out. So it is kg per second, that is the flow rate, right. So if we then substitute these values, if we substitute the given values, given our thickness is 1.7 millimeter, so that we can write 1.7 10 to the minus 3 meter, right. We are also given density rho as 820 kg per meter cube. We are given viscosity mu is equals to 0.2 Pascal second. So if that is true, then we substitute m dot is equals to del cube, that is 1.7 10 to the power minus 3 whole cube, rho 820 and g 9.81 and 3 into 0.2 Pascal second by 820, right. So this on simplification should give you 0.054, right, kg per meter per second per unit width, right, kg per meter per second. So kg meter square by second. So this was that kg meter square per second. So 1 this was out. So kg per meter second it remains. Yes, yes. So 0.054 kg per meter per second is the mass flow rate. Then Reynolds number we can say this to be equals to NRE. So that is 4 m dot by mu. So this Reynolds number also we had given in different forms. So one such is 4 m dot by mu, right. So that is 4 into 0.054 divided by mu is 0.2 Pascal second is equals to 1.08, right. So that means it is purely laminar, right. If you remember it, we said that with ripple and without ripple, right. We said with ripple and without ripple, the Reynolds number, if it is without ripple, then that is between less than 25. so far I remember. Less than 25 was the Reynolds number. So, Reynolds number, if it is less than 25, then we get okay, NAD less than 25, it should be, and then we can get that this is laminar flow. Third one was asked that what is the average velocity. What is the average velocity or V average, right? What is the average velocity or V average? If you remember that we had said, again this average velocity we had given into three forms. So, one was rho g del square by 3 mu, right? 1 g del rho g del square by 3 mu. So, it was 820, right, into g is 9.81, right, and del is 1.7 10 to the power minus 3 meter whole square divided by 3 into 0.2 Pascal second. So, this on simplification gives 0.037 meter per second, right. So, this way we can find out what is the Reynolds number, what is the velocity, what is the mass flow rate, given the different things, right. So, and if you remember, we had given in all in different forms. So, that mass flow rate also we can, that was volumetric flow rate, that was also determined, then mass flow rate, that was also determined. So, if we look at this, then we can say that this was like that, okay. And Reynolds number also we had given in different forms, and different forms like Reynolds number we had also given as 4 del V average rho by mu. This was also one Reynolds number, right, and we also gave that thickness del is equals to, in different forms, one was under root 3 mu V Z average, right, by rho g cos beta, right, and this was also under root 3 mu q by rho g w cos beta. So, here it is said unit width, so w will go out, and this was also given as, if you remember, cube root 3 mu m dot by rho. This was rho cube, right. This was rho cube root rho square g cos beta, right. So, this was for Reynolds number given, right, and if you remember that this q was also given as rho g w del square cos beta by 3 mu, right. So, that was like that, and we also gave that this to be average velocity, that we had also given that V average. This average velocity we also had given as rho g cos beta to del square by 3 mu. So, all these given, and we could find out the corresponding values, right. So, this is what we want to make, that when you have been given a given problem, so depending on the requirement you find out the relation, and then from that relation you can get whatever has been asked for, right. So, for example, here we had given all the necessary things, but if normally the density of this thing oil is very important to know in many cases, right. Suppose if we have the other values, so we can say like that, if the oil has the same problem 1.7 10 to the minus 3 meter thickness of the film, right, and if we say the viscosity of the oil was say 0.2 Pascal seconds, and if we say that the Reynolds number for the flow was say 16, right. Reynolds number for the flow was say 16, then how can we find out V average has say average velocity, average velocity say around 0.3 meter per second, right. Then find out that what is the density of the oil, right. So, in that case, first from the Reynolds number value we can find out 4 del V average, right, rho divided by mu, right. So, from this we can find out what is the value of density. So, Reynolds number given is 16, 4 del given is 1.7 10 to the minus 3 meter, right. Average velocity given 0.03 meter per second, right. So, rho to be found out, and viscosity 0.2 Pascal per Pascal second. So, in that case, if we say, then the rho becomes equals to 16 into 0.2 over 4 into 1.7 10 to the minus 3 into 0.03, so much your density. So, let us just use this is a one which we need a calculator, right. So, we have 16 into 0.2 divided by 4 into 1.7 into 0.03, right. So this becomes this, and so this is this times 100, this time 100, no, this time 1000, right, this times 1000. So much kg per meter cube, then somewhere something wrong might have been done, right. So what we have done wrong, you let us look into 4 into 1.7, 10 to the minus 3, right. 4 into 1.7, 10 to the minus 3, average velocity is given 0.03, that's what we saw meter per second. Density is so much, right, and viscosity, viscosity is, yes, 0.4. So so it becomes 16 into 0.23. Let us look into that, into 0.23, right. 4 del for V average rho by mu. So that is 16 given 4, 1.7 into minus 3, 0.03 rho by 0.2. So 16 into 0.2 by 4 into 1.7 into minus 3 into 0.03. Yes, we have not done anything wrong. So let us check the calculations once again, that where it has gone wrong, whether at all. So it was 16 into 0.2, right. This is so much divided by, it was 4 into 1.7 into 0.03, right, into 0.03. So it becomes this much. Oh, that is coming 15, and 10 to the 3, if that goes up, then it is 15,000. Though, then where did we do anything wrong? So V average Reynolds number is so much, right, and V average we found out is given 0.03, NRE is given that. Then where did we make the thing wrong, right? So Reynolds number is 4 del V average rho by mu. That is true. So if we do the other way around, if we find out, say, Reynolds numbers to be found out like the previous one, so 4 into 1.7 10 to the minus 3, right. Say here we had taken 820, and here we had taken 0.2. So under that situation, it becomes equal to, let us look into that, 4 into 1.7 right, 6.8 into 820, right, divided by 0.2 right. So, this divided by 1000, so 27.88 or 27.88. So, that means there is some turbulence with this value, right. There is some turbulence with this value, and because turbulence, not turbulence, there is some rippling like this, as we said that some rippling like this may happen, right. And after that, when if we take this, that Reynolds number to be okay, 27.88, 27.88 and 4, this is 1.7 10 to the power minus 5, 1.7 10 to the power minus 5, right. And average velocity we had taken how come this we had missed one, how come this you should have, okay, we had missed one. So, here the viscosity velocity also should have been taken, which we did not take. So, that is why it was coming. So, it was 0.03. So, into 0.03, .83, right. So, this value is 0.83 and 4 into 1.7, right, into 10 to the power minus 3 into 820 into 0.03, right, divided by 0.2. So, this was that divided by 1000. So, value is coming 0.836, and that is too low, too low. However, so what is needed is that generally for this kind of problems, this density is a physical property. So, that to be measured somewhere with some other devices, not with these kind of relations. With these kind of relations, we can easily find out like viscosity, like velocity, like Reynolds number, like thickness. These things can be easily found out, because other physical parameters, they are normally determined with the devices which are known, density, like density as you have seen, you can find out from specific gravity bottle. So, that value will be more accurate, and from there these physical properties are normally known. Similarly, viscosity also can be determined, as we have done in some class, that how can you predict the viscosity with a certain situation, right. Maybe in future also similar thing we will do, and but those are based on the relations exactly, right. So, try as much problems you can handle, and let us stop it today here. Good, thank you.